Why structures are designed to bend instead of break. The physics of structural flexibility. When we look at massive structures such as bridges, skyscrapers, dams, or airplane wings, we often assume that their strength comes from being completely rigid. Many people imagine that the safest structure is one that does not move at all. But in reality, engineers design most large structures to move slightly. Bridges can sway in the wind. Skyscrapers can gently lean during strong storms. Airplane wings bend dramatically during flight. Even large dams can experience small deformations when water pressure increases. At first glance, this might seem dangerous. After all, why would engineers intentionally allow structures to move? The answer lies in an important concept in physics and engineering known as structural flexibility. This principle allows structures to absorb forces safely instead of resisting them rigidly, which helps prevent catastrophic failure. Understanding structural flexibility reveals an important truth about engineering. Sometimes the safest structures are not the stiffest ones, but the ones that can adapt to forces acting upon them. Let's explore the fascinating physics behind this idea. What is structural flexibility? Structural flexibility refers to the ability of a structure to deform slightly under load without losing its strength or stability. Instead of remaining completely rigid, a flexible structure can bend, stretch, or sway within safe limits. When the force causing the deformation disappears, the structure returns to its original shape. This type of behavior is possible because of the elastic properties of materials. Materials like steel, aluminum, and certain types of reinforced concrete can temporarily change shape when forces are applied. As long as the deformation remains within the material's elastic range, the structure will recover once the force is removed. Engineers design structures carefully so that expected loads remain within this safe elastic range. This means structures can safely respond to environmental forces without permanent damage. The physics behind structural flexibility. The physics behind structural flexibility is based on several key concepts in mechanics. Elastic deformation. One of the most important ideas is elastic deformation. Elastic deformation occurs when a material changes shape under stress, but returns to its original form once the stress disappears. This behavior follows a principle known as Hooke's law, which states that the deformation of a material is proportional to the force applied to it, as long as the material remains within its elastic limit. In simple terms, if you stretch a spring slightly, it returns to its original length when released. Structural materials behave in a similar way when properly designed. This property allows buildings, bridges, and aircraft to handle forces safely. Stress and strain. Two important terms used in structural engineering are stress and strain. Stress describes the internal force within a material caused by external loads. It is typically measured as force per unit area. Strain describes how much a material deforms relative to its original size. When a structure experiences load, stress develops within its components, and strain measures how much those components stretch or compress. Flexible structures distribute stress across a wider area, reducing the risk that one part of the structure will experience excessive force. This distribution of stress is essential for structural safety. Why engineers avoid perfectly rigid structures. It might seem logical that the strongest structure would be completely rigid. However, perfectly rigid structures can actually be more dangerous. When a rigid structure encounters strong forces such as wind, earthquakes, or heavy loads, it has very little ability to absorb energy. Instead, stress concentrates in specific areas. If the stress exceeds the strength of the material, sudden cracking or structural failure can occur. Flexible structures behave differently. They absorb and distribute energy, allowing them to survive forces that might otherwise cause catastrophic damage. For this reason, engineers intentionally design flexibility into many large structures.
Structural flexibility in bridges. Bridges provide some of the most visible examples of structural flexibility. Long-span suspension bridges are designed to move in response to wind and traffic loads. In fact, it is normal for these bridges to sway slightly during strong storms. Some large bridges can move several meters sideways without sustaining damage. This movement allows the bridge to dissipate wind energy rather than resisting it rigidly. However, flexibility must be carefully controlled. A famous example of excessive structural movement occurred during the collapse of the Tacoma Narrows Bridge in the United States. The bridge experienced dramatic oscillations caused by wind-induced vibrations. Eventually, these oscillations grew so large that the structure failed. This event taught engineers valuable lessons about the importance of aerodynamics, vibration control, and damping systems in flexible structures. Today, bridge designs incorporate advanced aerodynamic features and energy-dissipating devices to prevent similar failures. The balance between strength and flexibility. While flexibility provides many benefits, engineers must carefully balance it with structural strength. Too little flexibility can cause brittle failure. Too much flexibility can lead to instability, excessive vibrations, or resonance. Successful structural design requires precise calculations and extensive testing to determine the optimal balance between stiffness and flexibility. Engineers use advanced computer models, wind tunnel experiments, and material testing to ensure structures perform safely under all expected conditions. This careful balance allows structures to remain strong while still responding safely to environmental forces.
Why structural flexibility matters. Structural flexibility is one of the most important concepts in modern engineering. It allows bridges to survive storms, skyscrapers to withstand wind, airplanes to endure flight forces, and buildings to resist earthquakes. Instead of fighting against nature, flexible structures work with physical forces, adapting to them safely. This approach reflects a deeper understanding of physics and material behavior. Rather than trying to create perfectly rigid structures, engineers design systems that can bend, absorb energy, and recover without damage. If you enjoy learning about physics, engineering, and how the world's greatest structures work, be sure to like, subscribe, and follow RE07 for more science and engineering explanations. Because here at RE07, we explore the physics behind the systems that power our world.